gears ever so slightly towards, we head towards lunch and begin several talks focusing on ultra-diffuse galaxies. The first of those being Romanowsky on the halos of UDG.
So I'm going to start by giving a bit of an overview of the field of UDGs, the fairly recent field, and then some new ideas, some new results. The original title was The Halos of Ultra-Diffuse Galaxies. I'm going to change it to something a little more provocative, which is ultra-diffuse galaxies are halos, question mark. So if you'll bear with me, I'm going to be trying to connect some dots here, some possible tenuous connections, but if you'll join me, take the red pill, and we'll see how deep the rabbit hole goes, and see if we can find some interesting ideas about these galaxies. Just to remark that some UC Santa Cruz people are collaborators on some of these projects. Ursula Labi, Gene Brody, and Viraj Pandya is going to be giving a talk shortly with some new results on UDGs. So where do UDGs come in? This is the state of the field when they were first recognized in 2015. This is a kind of a classical plot of effective radius versus luminosity, or absolute magnitude on the bottom. There's your luminosity on the top. And here we're cutting off the giant galaxies. This is plotting only spheroidal galaxies kind of for a more homogeneous comparison here. And there's this tail here of the giant ellipticals curving up to the dwarf ellipticals and the dwarf spheroidals, and the ultra-faint dwarfs are off the plot. They follow kind of this nice snaky smooth trend with maybe a few outliers here and there, compact and diffuse, that because they were rare, nobody really paid that much attention to them at the time. For example, these ones that Julian Del Conte found from a survey of low surface brightness objects, did some spectroscopic follow-up, found they're quiescent, these very large quiescent galaxies in the field. So enter the Dragonfly array using commercial telephoto lenses with these nice anti-reflective coatings to look at low surface brightness features. Bob Abraham and Peter van Dokkum were looking at the coma cluster. They were interested in the intercluster light, but they serendipitously found a bunch of these smudges, which they looked at in more detail, turned out to be these galaxies that nobody had. Some of them were in catalogs, but nobody had really noticed that they were unusual. So here they are on the same plot as before, these red dots up here, extending to higher effective radii. And I didn't mention earlier, these are the dashed lines are constant surface brightness. So as you go to the upper left in this diagram, that's the classic problem of running into detection problems, whether you're looking at Milky Way satellites, ultra-faints, or you're looking for these low surface things, brightness things farther away. So on this log-log plot, maybe that doesn't look like such an impressive difference, but if you look at the actual numbers here of a few kiloparsecs effective radius for a dwarf, that's about the same size as the Milky Way in the effective radius. So here's some characteristic parameters of these things. About, say, the brightest ones are about 10 to the 8th, so luminosities, getting up between 1.5 and 5 kiloparsecs in size, a surface index of 1, low surface brightness object. So they have luminosities like dwarfs, but sizes like giants, which raises the question of, well, what are these things exactly? One of the first things you'd like to know is the distances to these, and make sure that you really know the sizes and luminosities. There's various groups, including ours, that have been working on spectroscopic follow-up. This is a current status in the coma cluster, a phase space plot, and all these big things marked here are UDGs that are now spectroscopically confirmed. So there's no question these things are at the distance we think they are, and from spectra. Oh, I should mention that in coma there are about 200 of these objects now. We estimate about 200 UDGs. So it's a minority fraction of the galaxies, but it's a significant fraction. Okay, so here's just a pretty picture to show you to scale what this would look like if you saw it in the local group. There's M31, here's a dwarf elliptical, compact elliptical, which are similar luminosities to UDG, but the stars are spread out much farther. Mike Boylan-Colchin has talked about the Fornax dwarf spheroidal earlier in the week. There it is for the same scale. So the idea is this is like a giant Fornax dwarf spheroidal, maybe 10 times higher luminosity, similar surface brightness. And I'll talk about the globular clusters in a little bit. Moving beyond the coma cluster, we looked at the one of the Hubble Frontier Fields cluster. This is over 10 to the 15, several times 10 to the 15 mass cluster, looking at the ultra-diffuse galaxies, and there are tons of them based on the area we looked at. we think there's about 2,000 of those in this massive cluster. And a lot of groups have now been looking at this in clusters and groups, even in the field, looking at ultra-diffuse galaxies. You can start making scaling relations, and these numbers kind of wiggle around, but they tend to converge on a number of these galaxies is approximately linear with halo mass. At about 10 to the 13, you've got a couple of ultra-diffuse galaxies. So the local group is maybe expected to have 0 to 1 of these things. So what that tells us, the first thing it tells us here is that this is not a uniquely cluster phenomenon. People thought when we found these in the Coma cluster has to do something with ram pressure stripping, et cetera, but these are found in fairly low density environments, so there's something else going on here. Now looking at the distribution within a cluster, this is stacked a bunch of clusters here. This is the number density profile of UDGs in these stacked clusters, which follows this other line here is the rest of the galaxies. It follows those galaxies, except there's a core inside about a tenth of a virial radius, say 300 kiloparsecs, suggesting that they've been tidally disrupted in that region. So moving beyond clusters to the low density environment, it looks like beyond clusters, beyond groups, it's much harder to look for these things and confirm them, but it appears that they're found even beyond clusters and groups in the field. Here's one that our group worked on, which was originally thought to be a local group, dwarf spheroidal, but it turned out to be a very distant ultra-diffuse galaxy. Where the spectrum is quiescent. Viraj has some Spitzer analysis, which is finding the age is very old. So these are very old, based on a sample of one so far, these are old, large galaxies in the field. This particular one might in principle be a backsplash galaxy. It's sort of on the peripheries of a cluster, so that might be an exception. We've started looking at the gas content of these. This is the gas fraction, MH1 over stellar mass versus the stellar mass, and this is from the alfalfa survey. There's this trend as you go to lower masses, you get higher gas fractions. There's these things that people are calling blue EDGs, these are things marked in blue, which may or may not be the same thing, and they're consistent with following the same relation. These other ones we're calling red UDGs in the field. There's no point looking in clusters because these be stripped anyway. But in the field, you can look at this, and that one at least is no H1 detection. Two others we've looked at have no H1 detection, suggesting they're a different population. Although I say we're going to have this was a rapid publication, we may have a rapid retraction because we've got HST data on one of these, and that one's going to go away. Actually, the distance was wrong to that, so it's not a UDG. So any case, there's tentative suggestion from H1 and just the existence of these quiescent things in the field that there's two formation channels for UDGs possibly. One is just kind of taking these low surface brightness star-forming galaxies and just quenching them as they fall into groups and clusters, but the other may be something else that's quenching them even in the field. So, okay, just a quick summary of some of the main properties of ultra-diffuse galaxies. This is again the same plot on now a linear scale instead of a log scale. Okay, and generally they're undisturbed. They don't look like they're tidally disrupting systems on the red sequence. As far as we can tell, they're red and dead, although we need to get the ages more precisely. Spheroids, Andy Berker did some work showing their prolate spheroidals. We'd like to know what their metallicities are and what their halo masses are. And Viraj will talk about the metallicity topic. Okay, some preview of some formation scenarios. You'll hear about some of this after me. I'd say I'd like to lump the scenarios into two main classes so far. One is that both of them being that they're just ordinary dwarfs in some sense, but we're seeing kind of extreme cases. One is that they're just the tail of the spin distribution. The higher the halo spin, the larger your disk, the lower surface brightness object you've got. And if you work through the numbers of the halos and the number of halos with high spin and lambda CDM, you can get about the right number of ultra-diffuse galaxies in clusters. That's work from Amorisco and Loeb. Another scenario is that they are feedback expanded dwarfs from some kind of bursty feedback, as we've heard about already, I think about Nihao, also from Fire, that's a way to get these diffuse dwarfs, and they can look red and dead temporarily. They're still star forming, but they go through cycles of about, say, 2 gigayears, and so in the meantime they can fade, they can look red and dead. So what are some predictions from these scenarios? So generically, if you find these things in the field, they should be either star forming or temporarily quenched, but intermediate ages, because they're dwarfs. They still star form unless they've got a massive host. They're basically disks in origin, so you should be able to look at the morphology and kinematics to tell they had some diskiness, even if they've been puffed up a bit. They should be gas-rich in the field, which I already talked about. That could be an issue. They're just normal dwarfs. They should have normal dwarf halos. And implication from the Nihal simulations, it's great for apparently reproducing UDGs in some sense, but doesn't tend to produce normal dwarfs, which are most of the dwarfs. And I've seen that with a SAM analysis as well. This seems to be a possible generic problem, is that whatever explanation you come up with for one class of galaxies like the UDGs, make sure you're reproducing the other galaxies at the same time. Okay, so moving on to what I think is a really interesting constraint on UDGs. So far, from everything I've showed, it's a little bit hard to tell the difference between UDGs and normal dwarfs. Are they any distinction other than being big, low surface brightness? Well, globular clusters are another angle of attack, and these can be seen out to the coma cluster distance with both ground-based and space-based imaging. And you can do things like count the number of globular clusters, and you can measure the dynamics of the galaxies by taking spectra. So we've done that, and I won't talk too much about this, but we've taken spectra of globular clusters around this Virgo UDG and gotten the first dynamical mass of a UDG. Then now there's a total of 3 UDGs with dynamical masses. So what do you get when you look at just the photometric properties of the globular clusters in UDGs? So here are some coma UDGs with everything except the globular cluster candidates masked out. And you can see there's tons of these little point sources that are consistent with being globular clusters. If you looked at a normal dwarf at the same distance, you would only see a handful, maybe like 3, 5, something like that, similar luminosity. So that's kind of remarkable. Here's another way of showing that. This is the mass in the globular cluster system versus the stellar mass of the galaxy. The standard correlation is these gray points here, and the coma UDGs are up here, about order of magnitude more globular clusters at fixed stellar mass. The Fornax dwarf, we've already heard, is kind of a remarkable one for having 5 UDGs, but these things are more extreme even than Fornax at the same stellar mass. So for some specific comparisons, these 2 galaxies, they're about 2 times 10 to the 8 luminosity, 70 globular clusters each. And the Milky Way, of course, much more luminous, has only 160 globulars for comparison. But actually, I mean, these are, very pretty and interesting, but actually the ones that, if you get down here to the lower luminosities, they get even weirder. You might be able to see that there's 3 galaxies here, you might not. Mainly, you just see these globular clusters around them. So they're sort of like almost globular cluster only galaxies. So for numbers here, you've got a couple times 10 to the 7, similar luminosity to Fornax, except say 30 globular clusters each. Okay, Fornax luminosity dwarfs with 30 globular clusters.
Question?
Yes?
I must have missed it. Did you tell us anything about the colors or ages of these globulars?
We haven't done a lot of work on that. As far as we can tell, they roughly follow normal globular scaling relations for being old metal poor globular clusters. But there hasn't been much work done on that yet.
But they're not young?
No indication they're young, no. Which in cluster, this is a cluster environment, that would be weird if there's sort of any young stars, whether they're globular clusters or the field stars. Okay, so what do we learn from these globular clusters? Again, Mike talked about the Fornax dwarf, where there's 4 of the 5 globulars marked here. And this is close enough that you can actually compare the globular clusters to the field stars. And here's the metallicity distribution of field stars. Now, these histograms are not exactly normalized in the same way, but basically the globular clusters are very metal poor, most of them less than -2. And most of the field stars are more metal rich. There's a tail of them down here, which gives you all sorts of interesting constraints in globular cluster formation. But for some numbers here, in this Fornax, about 2% of the stellar masses in globular clusters, about 5% in the field stars that are presumably associated with those globular clusters, whether they dissolved globulars, evaporated, whatever. Now, if you look at these lower luminosity UDGs in coma, here's one where, again, you can't even see the field stars, just the globulars. Now, this is more extreme than Fornax. You have maybe 10 to 25% of the stellar mass in globular clusters. And if if you assume that the similar mass fraction here, that you've lost stars, had associated stars with globular clusters, you may have up to 100% of the stars in this galaxy associated with these globular clusters. It's basically a pure globular cluster galaxy, a pure stellar halo galaxy. Again, this is a little bit speculative until we run through it, but this seems to be the direction these observations are pointing. So one of the things you can test this by saying, okay, really, if these are pure stellar halos, then you'd like to know the colors, the metallicities, the ages of these to see if they're consistent, would be in the same as the globular clusters. Viraj will talk a little bit about that. One object he's looked at is this Virgo cluster dwarf, and it turns out the field stars are unusually metal poor for its luminosity. So it seems to be pointing in the right direction to be these pure stellar halos. Okay, now moving on a little even more controversially. This was some press we got on one of these things, dark twin of the Milky Way. Here is some other semi-fake news about being a galaxy full of devils. I'm not really sure why, but anyway, is Anatoly here? Maybe he could explain that. But this has to do partly with counting globular clusters. So this is just an empirical result that we don't really understand why yet, but if you look at the mass of the globular clusters versus the stellar mass, there's this kind of bend in the relation that you've got higher, more globular clusters at the high and low mass ends, the dwarfs and the BCGs, which is pretty similar to what you look at the halo to stellar mass relation, the same type of bend, which means that if you multiply that through the inverse, it cancels out that bend and you get the globular clusters versus the halo masses being a straight relation. So for some reason, they scale globular cluster mass scales with halo mass. Okay, which is a little bit weird. For one thing, globular clusters are not out of the virial radius. They're well inside, say, 1/10 of the virial radius typically. So they shouldn't really couple that well to the halo mass. Well, maybe it's just a secondary effect. They should really couple to the inner parts of the halo when the globular clusters form. And we've been able to test that. Bussola did some work with a slug survey to look at the dynamical masses in the inner halos about the halo scale radius, 10 effective radii, on individual galaxies, not just sort of average galaxies here, and found a really nice tight correlation between the globular cluster, the blue globular clusters, and the halo mass on that dark matter halo scale radius. So it kind of confirms this picture that we're seeing. So for some reason, the blue globular clusters in particular are associated with the inner parts of the dark matter halo. Okay, so let's go ahead and say, let's go down the rabbit hole and say, okay, let's say the UDGs follow the same relation as all the rest of the galaxies. They're not any different. And the fact that they've got overabundant in globular clusters by a factor of 10 would then suggest they're overmassive in the dark matter halos by a factor of 10. So here's the new halo to stellar mass relation with normal galaxies here. And here's Aldo's work, and there's many others that have a similar relation. It's kind of a standard relation there that follows that's actually globular clusters here calibrated to follow this relation. And then these UDGs would be overmassive. Okay, and I won't get into the dynamics. It's difficult to tell from dynamics so far, but it's consistent with this picture. So if you turn this into a star formation efficiency, the implication is at fixed halo mass, the UDGs are under luminous by a factor of 100. So something weird has apparently gone on. Consistent with this picture of that, when the globular clusters form, you've got this pure stellar halo, and then star formation just stops for some reason. These galaxies, for some reason, are not too big to fail. I don't know the physics of that, but just to kind of sketch that schematically, here's the stellar to halo mass versus redshift. This is again with all those models for a typical halo here of 10 to the 11.5. Now, with a UDG, the idea might be that, okay, it stops forming stars back here at high redshift, say 4 to 7, maybe through mergers or just isolation. It kind of does this track and you get a UDG. What's nice about this is it fits in nicely with what we think we know about globular clusters at the moment, that this is where metal poor globular clusters form. Metal rich ones are a little later, which the UDGs don't seem to have anyway, as far as we can tell. So there seems to be some association with the metal poor globulars form about the right redshift to turn off the star formation to give you about the right halo masses to reproduce the number of globulars. Just to remind people that you can just count the number of globular clusters around galaxies in the nearby universe. And we know if we form them at this redshift, they end up, there's a lot of stars, so that's most of the stars of that redshift. Or sorry, not most of the stars, but a large fraction of the stars. Which ties into this idea that maybe globular clusters, we've heard that about this already, maybe globular clusters are sources of reionization But not only globular clusters, but maybe the UDGs are the host for those globular clusters. So the UDGs themselves are one of the main sources of reionization. And then why they quenched, it would have to be probably some kind of self-quenching through extreme feedback and not reaccreting gas. So that's, be nice to hear any ideas for why that might happen. But in any case, that these UDGs would be fossils of early galaxy and globular cluster formation epoch. These are the ones, a lot of them fell into other galaxy halos and formed those halos, but some of them survived and we can still see them. So, okay, in summary, are UDGs halos? There's this novel class of galaxies that don't fit in with what we previously knew. They may be failed galaxies or pure stellar halos, so there's some kind of fossils from the reionization era, perhaps, that some of them went into the halos of massive galaxies, formed the globular cluster systems and metal poor stars. So now you've got these things with lots of globulars and few stars. That means these are key systems for understanding globular cluster formation. They're also key systems for using globulars to understand their formation. And just to keep in mind that globular clusters are supposed to form in very high density gas pockets, and these are the lowest surface brightness galaxies, so it's sort of a contradiction. So that feeds into the idea that maybe they were compact and they've expanded. So that part of one of the scenarios is consistent. And this may also tell us something about the scatter and the stellar halo mass relation, but at a much more massive end of the relation. So it's not clear why it would happen at these halo masses about above 10 to the 11. So thanks for your attention.
Could it be that the mechanism that is quenching star formation in the UDGs have to do with the fact that they're in a cluster environment? So they're stuck. Probably if they were in the field, they would be gas rich, and if they were younger and with all the properties of more useful. So what's the role of the fact that they are in clusters?
Well, so they're not just in clusters. That's one of the first things people thought, oh, these are in the coma cluster. They got ram pressure stripped early, and that's why they look the way they do. But they're found in groups, even in the field now. So that's why I mentioned that it looks like there needs to be some other quenching process, particularly to stop star formation. There's a lot of globular clusters and few associated field stars. So something to stop them doing that, even in group environment where they fell in later, they should have continued forming stars for a longer period. That's a possibility. I mean, you do need to, yeah, so there's both a formation efficiency and survival fraction of globular clusters you have to put into if you want to start looking at the details of the models. So that's sort of yeah, that's an interesting question. Yeah. Avishai?
I wonder if you have any theoretical ideas of how to form the globular clusters, how to make everything go into the globular clusters, how to make them all break down and express, how to make everything expand. Do you have any physical information?
Well, I mean, I think what you're seeing in the Nihao simulations, it seems like sort of pointing in the right direction, that you've got some strong feedback episode that when you form the globulars in these high density regions, a big burst of star formation, and you can puff up your galaxy. My question would be then, why do you not keep forming stars after that? You know, you puff it up, but then the gas keeps falling in, and why do you not keep building up your galaxy?
But you're talking about the gas in the very early phase, right? Making the stars in the globular clusters. There's no more. If I understand correctly, your scenario is the opposite of our scenario.
In the sense of the timing, yeah.
In the sense of everything.
Yeah. Okay.
Massive halos, we talk about normal halos. We talk about gas processes at later time. You talk about something that happened in the dinosaurs time.
Yeah. Maybe, yeah. I mean, you do have a peak of star formation at early times, right?
Maybe I should think about it.
Yeah.
I really want to have any clue for how this can happen.
Yeah. Well, I would too. Yeah.
Let's think about it.
Okay.
All right, well, let's thank Gary again.